Hello, good evening, all of you. I'm Soman. I would be taking Basics of Biostatistics-3. Today's topic is statistical inference. So let me do a little recap for you. Last class, I spoke about normal distribution and informed you all that the data with a normal distribution lies in three standard deviations from the mean on either side of the normal curve. And I also explained you about Z-scores, and I also explained you how Z-score are related with normal distribution and with standard deviations. Now, the whole area under the curve of normal distribution equals to 1, and the midpoint of the normal distribution or the curve of the normal distribution indicates mean, median, mode lie at that same line. And now the whole data, the percentage of data which is included in first standard deviation on either side is 68%, and on two standard deviation it is somewhere around 95%, and towards the end of the three standard deviations it is about 99.7%. So the percentage of data which is held in each standard deviation is known to you, and we even calculated probabilities in different examples using Z-scores. Now when you calculate Z-score, you will get to know the position of the data from the mean in the normal curve. So you know about standard deviation, you know about normal deviation, you know about Z-scores. Now we would do some application of Z-scores, and for an example I would like to give you all here is Z-scores help in giving meaning to the data in a statistical quantitative way. All of you are familiar with heart rate, and all of you are familiar with normal heart rate in adults. Let's take an example. If a patient has a pulse rate of 58 beats per minute, what implication does it have if you don't know the normal value? What information does the patient's heartbeat tells you if you don't know what is the normal value of heart rate? The implication of that value is evident only if you know where the score falls in relation to the distribution of normal pulse rates. So now if we know the distribution of normal pulse rate, and in this example, we know that an individual has a 58, that is one standard deviation below the mean. Our mean heart rate is somewhere around 72 beats per minute, and when you calculate the Z scores, you will find out that 58 lies in one standard deviation below the mean. Now this gives us a clear interpretation. Now that you know where the position of this person's heart rate is in a normal distribution, or you know when you compare it with the normal, you know that the person's heart rate is less than the normal or more than the normal. So now we express this score in terms of Z scores, and that gives you standard deviation units. So now if you have minus standard deviation units, that means the person's heart rate, that is of 58, is lying on the opposite side, that is towards the lesser side of the normal heart rate. And if the Z score is positive, that means it is lying towards the positive side or higher than the norms of the heart rate. So a score of 88 is now transformed to Z score, and it will give you a value of 2 standard deviations above the mean. Now how to calculate all these standard deviations or Z scores has been taken in the last webinar, and how to read the Z table has also been told in the last webinar. So when I put up the material for reading, I think you should go through it and you would be able to appreciate much better. Now, another term I would like to introduce after you have known about normal distribution and Z-scores and standard deviation is hypothesis. Now, hypothesis is just a statement. It's a question which is in your mind, or it is the explanation you give for a certain phenomena which has not been proven. So now in statistics, you have to prove this phenomena or you have got this question in mind, and the results can be whether your hypothesis is true or not. So for this reason, we have two types of hypothesis. I'm sure you must have heard about a hypothesis in your biostatistics classes in your masters. So now there is one hypothesis that's known as null hypothesis, and it's denoted by HO, and it means that this hypothesis has no difference. That is, it is hypothesis of no difference. We define null hypothesis for each study question clearly before we start the study. Now the alternate hypothesis is denoted by H1 and it's opposite of null hypothesis, and in plain language terms it is the hypothesis that is what we are trying to investigate in comparison to null hypothesis. So null hypothesis means there is no difference between the two groups, and the alternate hypothesis says that there is difference between the two groups or whichever is in question. So for example, if the question is about difference in the blood pressures, so the alternate hypothesis will be that there is significant difference in blood pressures between groups A and B, and if we give group A the test drug and B sugar pill, the alternative hypothesis should be that there is difference in blood pressures between group A and group B if we give group A the test drug and group B a placebo, that's a sugar pill. So now this is in short meaning of hypothesis in statistics. Uh, we have got null hypothesis and we have got alternate hypothesis. Now, why it is necessary to state null hypothesis and alternate hypothesis? Now, um, whenever you set out to study a phenomena or you set out to study a question or the effect of intervention in some kind of disorder or a disease, or any condition, you need to state null hypothesis that um, there is no difference or there would be no difference between um, your intervention, that is experimental intervention, and the normal procedure or the control group. And your alternate, and you have to state your alternate hypothesis. Based on these two hypotheses would be your interpretation of the data. That is whether you need to take a double-sided test or single-sided test. Um, I don't think there is much question over two-tailed and one-tailed test. I think it's not important for you right now. I would try to explain it later when I'm talking about parametric and non-parametric statistics. Now, there are two types of mistakes in statistics, documented mistakes. There is a third type known as type 3, but it has no relevance with these two main mistakes which we would be talking about, and I'm sure you must have heard about it many times in your master's class. There is type 1 error and there is type 2 error. Now, we use inferential statistics to tell us about the true state of the world. Now we are trying to see whether our experimental manipulation has some kind of effect or not. And we have two possibilities in the real world. That is, one is our experimental manipulation has actually made a difference to our samples. Second possibility can be our experimental manipulation has no effect whatsoever on the groups or the samples. Now we look at this statistics and their associated probability, and we come to know which of the two is likely. So it is important that we are accurate as possible since we don't want to commit mistakes, and we need to find out whether our experiment has truly made an impact on the experimental group when compared with the control group. So these two types of errors are known as type 1 and type 2 errors. And I would tell you a memoir how to remember type 1 and type 2 errors. Um, just remember that our cynical society rejects before it accepts. So we'll be talking about rejection of null hypothesis in type 1 error, and we would be talking about acceptance of null hypothesis in type 2 error. Now, type 1 error is false rejection of the null hypothesis in short, and type 2 error is false acceptance of null hypothesis. Now, when we look into detail, just have a look at this figure which is given on the slide, and you would see the truth on the columns, whether it is true or not. And on the left hand side, you look at the decision, that is rejection of null hypothesis or do not reject null hypothesis. And in the truth column, you will see null hypothesis is true and null hypothesis is false. So now if null hypothesis is true and you reject it, it's type 1 error and it is denoted by alpha. Now if null hypothesis is false and you reject null hypothesis, then it is correct. You have not committed an error. Now when null hypothesis is true and you do not reject null hypothesis, that is also a correct decision. And when null hypothesis is false and you accept the null hypothesis, that is you do not reject the null hypothesis, then you have committed type 2 errors. That it is denoted by beta. So now you know that probability ranges from 0 to 1. I would be talking about probability in further slides. Now let me explain you type 1 error a little bit in detail. Um, this happens when we believe that our experimental manipulation has been successful when in fact it has no influence on experimental group. So in the real world, this would occur when our experimental manipulation has no effect, yet we have got a large test statistic because we selected two very dissimilar samples, and this happens most of the time in randomized controlled trials, and this is the most common mistake we commit in our master's thesis or any of the research topic we choose in our institutes, just because we do not try to find out difference between we do not try to see whether any difference exists between the control and the experimental group, and the probability of the error is 0.05, then the experiment has no effect. So the type 1 error is always known, that it is alpha level denoted by alpha. This is always known when you calculate sample size. So now you would be able to think a little bit in terms of sample size and type 1 error. So if you don't take enough sample size, you may not be able to justify whether experimental influence is there on the groups or not. Now type 2 error is happens when our experimental manipulation has failed, when the reality is it has not failed. So when this occurs, it occurs in the real world experimental uh, scenarios, and sometimes we record that the experimental manipulation did not have an effect on our experimental group. Because we obtain small test statistics, because it can be possible because of many variations. Variation can be in the reading of the values from the instrument, or the instrument has undergone any error, or if there was natural variability in the organism or any of the group. And that's how we recorded wrong data and we got very less test statistic. So the sample means appear to be quite similar, even though the experiment has made significant differences to the samples. And most of the time you must have seen in your own studies that there are individual differences in the samples, but the result which comes out finally shows you that there is no significant difference. We'll talk about the significance later. Now in an ideal world, we want to know the probability of this error to be very small. So Cohen in 1992 suggested that the maximum acceptable probability of type 2 error should be 20%. This is called as beta level. I hope you must have heard about it. You must have heard about power, that is 80%, that is 1 minus beta. So if you consider it as if you have done 100 experiments, out of that you will fail to find effect in 20 of those experiments. Or you take another example, that if you take 100 samples and you have done a genuine experiment, you would fail to find effect in 20 of those samples. So that's the basic reason why we have kept beta as zero point 0.2 or 20%. Now let's talk about probability. Um, I'm sure you must be having a question why we always consider 95% confidence interval, or why we pick up a value of 0.05. So when given all possible outcomes, the likelihood that any outcome will occur is known as probability. And when we talk about hypothesis, we can never be completely sure that either hypothesis is correct. So we end up working with probabilities. So we calculate the probability that results we have obtained are chance results, and as the probability decreases, we gain greater confidence that the experimental hypothesis is actually correct and that null hypothesis can be rejected. Now, most of you would be having a question, how did you arrive, how did we arrive at this p equals to 0.05, and why it is considered, why the probability is considered as significant when the value is less than 0.05. Now, if you break down 0.05, it comes out to be 5%. And if you break down 1 minus 0.05, it comes down to 95%. So Fisher suggested that we should use 95% as a threshold for confidence. And only when we are 95% certain that a result is genuine, that is, it's not a chance finding, we should be accepting this result. Now, opposite way to look at this is to say that if there is only 5% probability of something occurring by chance, then we accept that it is a true finding. So if I want to simplify this statement for you, we are looking at a result which should arrive genuinely by our experimental manipulation and not be having by chance. So the criterion of 95% confidence forms the basis of modern statistics, and there is very little justification about it, why it is so, other than Fisher. But just because R.A. Fisher said so, we have taken as a threshold for the confidence as 95%. Now, if the p-value is less than the chosen significance level, then you reject the null hypothesis. That is, you accept that your sample gives reasonable evidence to pick up alternate hypothesis or accept alternate hypothesis. It does not mean that there is meaningful or important difference or clinical difference in the real world. So most of you might get a significant result. That does not mean that in real or clinical world, your experiment has really made an impact. For that purpose, we would be talking about effect sizes and MCIDs later on. And for this reason also we compute confidence intervals. So nowadays the journal editors require you to present your test statistic along with the significance values and confidence intervals if possible. And if you give an effect size, that is added benefit. All this exercise is to estimate if there is clinically meaningful difference in the real world. Now the term significance level, we use it as alpha and we use it for P also. So it means that when we talk about alpha, it is a pre-chosen probability that is at 95% level of alpha. We calculate our sample sizes. And the term p-value is used to indicate a probability that you calculate after a given study, after choosing those samples where you have put significance level of alpha is 1.96. Now from where we get this 1.96, this 1.96 value is taken from the tables, and it is directly linked with ZScore. So we use probability in research as a guideline to make decision how well our sample data is showing the characteristics of a population. So we use probabilities to determine if observed treatment differences are likely to be representative of population differences or if they have occurred by chance. Um, uh, let's talk about what Fisher had to say about it. Now we use Fisher criterion of 5% that is expressed as a probability value of 0.05. And Fisher says that if probability of the two samples from the same population is less than or equal to 0.05, then we reject the null hypothesis and accept our experimental manipulation to be successful. Now, another term I would like to introduce you to you here is standard error of mean. Now, in the last slide, I had spoken about confidence intervals. In order to depict um, real differences or a true benefit in clinical scenarios, we need to calculate confidence intervals. Now, for that reason, you would need standard error of mean. Now, standard error of mean estimates the variability between sample mean that you have obtained when you take um, multiple samples from the same population. So it's given by standard deviation upon root n. N is the number samples you have taken from the population. And just to give an example, I would give you an example here about delivery of pizzas, or I would talk about some kind of delivery of a parcel. Let's take mean delivery time of 3.80 days, and the standard deviation of this delivery is 1.43 days. You can take this example of delivery in speed post, and this information is based on a random sample of 312 delivery times. So what this number indicates, now when we calculate standard error of mean, that is 1.43 divided by a square root of 312, we see that the random samples of same size and from the same population will always bear a sample mean of 0.08 days, or that is the standard error of 0.08 days. So this suggests that whenever we draw samples from this population, uh, we have committed very less error, or that is the sample mean which we have calculated after taking the samples from this particular population are uniform. So now we use standard error of mean to determine precisely the mean of sample estimates of the population mean. So lower values of standard error of mean will indicate that your estimate is precisely showing the population mean, or your sample estimate or sample mean estimate is generalized to the population mean. And when you have a larger standard deviation, you have large standard error of mean associated with it, and the sample mean which you derive from the samples which you take from the population, they do not precisely estimate the characteristics of the population. So always remember, when you have large standard deviation, you will have large standard error of mean, and the more what you say, the less likely is that the sample mean representative of population mean. So how can you overcome this problem? You can overcome this problem by larger sample size, and when you take larger sample size, it results in smaller standard error of mean, and you tend to have more precise estimate. Now, when we talk about confidence intervals, it's a range of scores with some boundaries. You must have heard about range of errors associated with any instrument, plus minus 5 or something like that. You must have heard that goniometry, that is used to measure joint range of motion, has error of 5 to 10 degrees. So you talk about plus minus 5 degrees. Okay, so you may get 5 degrees higher, or you may get 5 degrees less. Confidence interval is scores with specific boundaries, and these are known as confidence limits, and they would they contain values of population mean, or that or which represents they contain the values which represents the population. So confidence interval consists of values that act as good estimates of a population parameter, and the boundaries of confidence interval are based on sample mean and standard error. So again, if you have to take care about the standard error of standard error of means, and you have to take care of standard deviation, because if your standard deviation is large, it will give a bigger standard error of mean, and it will give you very narrow confidence intervals. So in short, wider the interval, the more confident we will be that the true population mean is in those confidence intervals. So the degree of confidence which we express uh, in confidence intervals is usually placed at 95% confidence. And we obtain boundaries of confidence interval using this formula, Ci equals to x bar plus minus z into sample standard error of mean. So this z value is usually denoted as 1.96. Um, and for our data here, I have taken an example. You would see how I have calculated the confidence interval for a particular thing. So whatever you compute, you have to add and minus it, subtract it. So you will get a range. After adding up, you will get the highest boundary, and after subtracting the number, you get the lesser boundary. So at the end, you will see 95% of confidence interval. You will see these two numbers. You can put a comma between them, or you can put a hyphen between them. Now, coming to the end of this webinar, I would be just touching upon parametric versus non-parametric statistics. Now is the right time to introduce this terminology to you all, because in next webinar, I will be talking about parametric tests and non-parametric tests. I hope you are eagerly waiting for uh, those. Now, statistics that are used to estimate population parameters are called as parametric statistics. More simply, if I want to put it, then it just means that when the sample follows normal distribution, we conduct parametric statistics. And when the data does not follow normal distribution, we usually conduct non-parametric statistics. But if you try to look in other ways, if the information from your sample does not represent the population, then you cannot do parametric tests of significance or parametric tests of hypothesis testing. So this normal distribution is the characteristic of data which we need to test every time before we do any analysis. And the validity of parametric tests depends on the assumptions of the data. So the primary assumption is that samples should be randomly drawn from the population with normal distributions. And the sample should be a useful representation of population parameters. And when you take small samples or with distributions that are not random or that are not representing the whole population, then it is not good to conduct a parametric test. Now, tests of goodness of fit can also be performed to determine how well a data matches the normal distribution. And the other assumptions are that the variances in the sample should be compared and they should be equal or homogeneous. We will talk about Levin's test, and we'll talk about a test of equal variances. Now, third assumption is that the data should be measured on interval or ratio scales, and therefore the scores can be subjected to arithmetic manipulations to calculate mean and standard deviations. Now, when statistical conditions do not meet the above requirements, we use non-parametric tests. Now, non-parametric tests take fewer assumptions about population data and can be used when normality and homogeneity of variance criteria are not satisfied. So they can be used effectively on smaller samples. So when you have a smaller sample less than 30, then it's always better to use non-parametric tests of significance. Well, the statisticians have not laid down any absolute rules for using parametric and non-parametric procedures, but I want to tell you that there are some statisticians who like to do parametric testing on some kind of ordinal scales, ordinal numbers. But the classical statistician will insist that all the assumptions behind parametric tests should be met and non-parametric tests should be used for ordinal scales. Uh, we'll talk about it when we talk about analysis of scales. Now, parametric tests are considered to be robust, and many kinds of statistics can be applied, and whatever the result comes out can be generalized to the whole population from where the sample was collected. But it is not possible in non-parametric tests. And sometimes we push these parametric tests to a limit because small violations are accepted in parametric tests, and it does not affect the validity of statistical outcomes. And that's why most of the statisticians use it for computation of ordinal data when they calculate scores from the scales. All the stuff we would be talking about in our next seminars. Now on Sunday, I would be talking about parametric and non-parametric tests in detail. And one by one, we would be talking about the tests. And we would be talking about their implication in rehabilitation. So to conclude, in order to conclude this webinar, I would just give you a quick recap. We spoke about implications of normal distribution. We spoke about hypothesis testing. We spoke about type 1 and type 2 error in great detail. And you came to know about probability. And you also know that if you even get a significant result, it does not mean that your intervention or your experimental manipulation on the samples has yielded clinically useful results. So when you want to say that your intervention has produced clinically significant results, you need to look at confidence intervals, you need to look at effect sizes. Then I told you about how to calculate confidence intervals using sample error of means, standard error of mean, sorry. Uh, and then I introduced you to the concept that why we have chosen p-value as 0.05, and just because Dr. Arif Fisher told us to, there is not much justification to it why we have taken it, and it would be clearer if you read the literature. So that's all for today. Have a good day. Good night.